We continue our discussion of entropy in 16.2. We've already sort of defined entropy as being some sort of measure of disorder, but we also want to be able to explain the relationship between entropy and the number of microstates. Microstates will be introduced here in a few minutes. I want to introduce the term reversible process. A reversible process refers to the process that takes place at such a slow rate that it is always at equilibrium, and its direction can be changed, or reversed, by an infinitesimally small change. And so, a reversible process, you really don't find these around in nature. Most things that we see are irreversible processes. Things aren't always at equilibrium. And we see this Q rev, reversible process, sort of buried in this equation from the last video. Delta S is equal to Q over T. It says here that the entropy change for a real irreversible process is going to be equal to that for the theoretical reversible process that involves some final and initial state. Let's talk about microstates. Following the work of Carnot and Clausius, Ludwig Boltzmann, who was very famous for his work in thermodynamics, developed a molecular scale statistical model that related the entropy of a system to the number of microstates possible for the system. So here we define a microstate, and we're going to label this with a W. A microstate is a specific configuration of the locations and energies of the atoms or molecules that comprise a system like the following. So here we have S for entropy, K is some scaling factor, natural log of W, the microstate. Here, K is going to be the Boltzmann constant. It has a value of 1.38 times 10 to the negative 23rd joules per Kelvin. As for the other state functions, the change in entropy for a process is the difference between the final state and the initial state. And so down below we see that delta S is simply the entropy of the final state minus the entropy of the initial state. But we've defined S up above as being the Boltzmann constant times the natural log of W, W being the microstate, so we can substitute those in. By looking at our log identities, we can go ahead and realize that this equation right here is equivalent to this one on the right, where K times the natural log of WF, the microstate in the final state, divided by the microstate in the initial state. For processes involving an increase in the number of microstates, that is, your final number of microstates is greater than the initial number of microstates, the entropy of the system increases. Therefore, delta S would be greater than 0. Conversely, processes that reduce the number of microstates, that is, the number of final microstates is going to be less than the number of initial microstates, yield a decrease in system entropy, and here we represent that as delta S being less than 0. This molecular scale interpretation of entropy provides a link to provide the probability that a process will occur as illustrated in the next paragraphs. So let us consider the general case of a system comprised of n particles distributed among n, little n, boxes. The number of microstates possible for such a system is little n to the big N. So that would be the number of boxes raised to the power of big N, which is the number of particles, as said right here. For example, distributing 4 particles among 2 boxes will result in 2 to the 4th, or 16, different microstates as illustrated down below, which we can see in figure 16.8. Microstates with equivalent particle arrangements, not considering individual particle identities, are grouped together and are called distributions. So if we look down here below, we can see, and I'll give an example of this. Look at A here in figure 16.8. Here you've got 4 particles in one box and 0 particles in the other box. And if you were to look at all the different combination of particles and boxes in the statistical representation, you would realize that there is one state that denotes 4 of these particles in one particular box, and the other box being empty. And so it is all by itself over here in A. And if you look at E, this is by itself because the 4 particles are in a different box, and the original box that we were considering that was full is now empty. And if you look at all of the different arrangements of particles in boxes, you will see that the most probable arrangement of particles in these 2 boxes is going to be listed here in C, as there are 1, 2, 3, 4, 5, 6 different microstates for this arrangement of particles in boxes. What's important to point out here is this last statement. Since entropy increases logarithmically with the number of microstates, right here, the most probable distribution is therefore the one of greatest entropy. So again, looking at all these boxes, what do you think will be the most probable distribution of particles in these two boxes? You guessed it, it's going to be this middle column C right here, where we've got two particles in each box. We get the largest number of arrangements of these types of particles in these two boxes if we were to look at this particular distribution. Your book says for this system, the most probable configuration is one of the 6 microstates associated with distribution C, where the particles are evenly distributed between the boxes. That is, a configuration of 2 particles in each box. The probability of finding the system in this configuration will be 6 out of 16. Again, we've got 6 arrangements for this particular configuration out of a total of 16 arrangements overall. That reduces down to 3/8. The least probable configuration of the system is one in which all 4 particles are in one box, and this corresponds to configuration A and configuration E, where the probability of finding all 4 particles in only one box is going to be 2/16, or 1/8. As you add more particles to the system, the number of possible microstates increases exponentially. That's 2 to the n. A macrostate, such as laboratory-sized system, would typically consist of moles of particles instead of just 2 to the n. And here, n would be on the order of 10 to the 23rd. And the corresponding number of microstates would be staggeringly huge. Regardless of the number of particles in the system, however, the distributions in which roughly equal numbers of particles are found in each box are always the most probable configurations. You should go ahead and finish reading this section, as it provides a pretty decent narrative on microstates and entropy. It continues its conversation by giving other examples and figures that will help allow you to better understand what is going on here. Finally, when you're done, take a look at example 16.2 and make sure that you thoroughly understand the content.